Assalamu alaikum everyone. So let's start with the second lecture in the series, which is in continuation of linear measurement. So we'll be talking about mainly chain surveying and specifically about using measuring tape. So the principle of chain surveying is triangulation. So I'll be talking about triangulation in my next lecture in detail. So triangulation is basically when you divide the area that you want to survey into a number of triangles. So basically, when you perform survey on the land, that means that you want to create horizontal and vertical control. What that means is that you want to set out different points whose horizontal distances or angles from a reference point and whose reduced levels. That means their height above a specific point is known. So in triangulation, what we do is we divide the area into a number of triangles, and basically dividing the area into a number of triangles gives you the leverage of using mathematical equations to find out different lengths without actually measuring them. So by using, let's say, trigonometric ratios, by measuring a few angles and few lengths, you can then determine a number of lengths because the whole area is in the form of triangles. So instead of measuring every length yourself, you can really fasten up the work by calculating them using mathematical relations. So when you divide the area into a number of triangles, it is recommended that you make well-conditioned triangles and not ill-conditioned ones. So well-conditioned triangles are the one in which all the angles are between 30 degrees and 120 degrees. And if one of those angles is lesser than 30 degrees or more than 120 degrees, that means your triangle is now ill-conditioned. So the benefit of using well-conditioned triangles is that if you are carrying an error in your measurements, the effect will be minimized if your triangles are well-conditioned. And if they're ill-conditioned, then the error will be maximized. So before we carry out triangulation, you need to make sure that the measurements you take with your measuring tape are correct. That means you need to apply a number of corrections on that measurement, and those corrections depend on your measuring tape. So there are two errors that we usually talk about. Uh, let's explain it like this. So if let's say that your measuring tape is of 30 meters, that means when you measure a length on ground in full extension of your measuring tape, the distance should be 30 meters. If let's say that your measuring tape says that the distance is 30 meters, while in actual it is measuring a distance more than 30 meters, that means your measuring tape is too long. On the contrary, if you measure a distance and your measuring tape says that you're measuring 30 meters, while in actually you're measuring something lesser than that, that means your measuring tape is too short. And that distance, which it is measuring lesser or more, that is the distance which is too short or too long. So first we need to see if our measuring tape is working correctly, is in the right condition. So for that, the method is that you use test gauge. That means you install two pegs in the ground, and the distance is known to be 20 meters or 30 meters, whatever you want to keep it. And then you place your measuring tape at zero over here, and then you measure this distance. If your measuring tape tells you that the distance is 20 meters or 30 meters, that means it is working rightly. If it gives you a distance lesser than or more than that, that means there is some error in the measuring tape and you need to correct it. Usually there is an error and you need to perform some corrections, and we'll talk specifically about those corrections. But before that, just a quick slide about scale for maps. So you already have worked with scales in your drawing course. So the scale for a map is given by a representative factor. So that means if 1 centimeter on map represents 10 meter on the ground, then the factor is given just by equating that. 10 meter on ground is equal to 1 centimeter on the map. So that means you have a representation factor of 1 over 1000. So um, from that you get the definition of a map or the distinction of a map, if it is a large scale map or a small scale map. So if the RF factor is between is less than 1 is to 500, that means it's a large scale map. Otherwise, it is considered to be a small scale map. So if this factor is greater than 1 is to 500, that means it is a small scale map. So what does it mean specifically? 1 is to 500 means that whatever units you're using, so 1 fit on the map or 1 inch on the map is equal to 500 something on gram. So if it is in this range, that means it is a large scale map. The reduction factor you are using is smaller. And on the other hand, if it's a large value, so let's say it's 1 is to 1000, so that means 1 millimeter on the map, whatever units, is equal to 1000 millimeters on the ground. So that would make it a small scale map because you are using a larger reduction factor. So coming to the corrections that you have to apply on your measuring tape. Before that, we need to make a distinction if you are using the measuring tape on a level ground or if you're using it on a sloping ground, because that brings in another correction that you need to apply, that would be the slope correction. So let's say we are doing it on a level ground. So this is the starting point and this is the ending point, and you are, let's say, doing ranging. You need to put up these intermediate points, and you want to put up these points at exactly 30 meters. So before that, you need to make sure that if your measuring tape is telling you that it is measuring 30 meters, if that is exactly 30 meters on the ground. So the number of errors that can arise are due to different factors. So the first factor that we will consider is the temperature correction. So since the material for the tape is steel, and with change in temperature, the steel can uh, expand or contract. So if it does that, that means the scale of the measuring tape gets disturbed. And how much is it expands or contracts depends on the coefficient of thermal expansion. So that is usually constant for any material. So whichever tape you're using, it comes with the manufacturer's note, which tells you what is the coefficient of expansion and at what temperature is the tape standardized. So that is the temperature on which the tape is exactly similar to what the manufacturer has manufactured it to be. If the temperature is more or less than that temperature on which it is standardized, then you will have these problems and you need to apply the correction. So the correction for temperature is given by this equation where CT represents the correction for temperature. Uh, its units are meters. You can use it in other units as well. Tm over here is the temperature at during measurement. So when you are using the tape in the field, you need to have a thermometer or some other temperature gauging instrument that will tell you that what is the temperature in the field at that time. So you measure that, and that would be Tm. T naught is the temperature at which the tape was manufactured or the tape was standardized. So that would be given by the manufacturer, and that is T naught. L is the length of the tape, the total length of the tape, not the length that you are measuring, but the total length of the tape. So if the maximum length of the tape is 30 meters, you would use 30 over here. And alpha is the coefficient of thermal expansion, which again depends on the material, which will be given to you. So using this equation, you can calculate the correction which is for temperature. Similarly, the next correction that you need to apply is the pull correction. So when you are taking a measurement with the measuring tape, you place it at the initial point, and at the final point you have a hook with the measuring tape on which you apply the pull. So you must have noticed that when you hold the measuring tape at an elevation, there is a sag in the measuring tape, and when you apply the pull, that sag keeps on diminishing. So if you keep on applying the pull, the tape keeps on expanding longitudinally like a rubber. So when it stretches, that means error is introduced in that measurement. And how much that stretches on what amount of force you're applying, that depends on modulus of elasticity or Young's modulus of the material. So which is basically stress over strain. So different materials will stretch differently on the same amount of force that you're applying on the end. So if you are applying this longitudinal force, which is the pull, it will stretch in the longitudinal direction and it will contract in the other direction. And the amount depends on modulus of elasticity. So this is the correction equation that we apply for pull, where Cp is the pull correction. Pm is the amount of pull that you apply while you take the measurement. And how do we measure the amount of force that we're applying? We usually do that using a spring balance. So by attaching a spring balance on the end and then applying the force through the spring balance. The spring balance can be digital or it can be the other one. So it will tell you what amount of force you're applying. P naught is the amount of force on which the tape was standardized and the recommended force that you should apply. So if you are applying the force in the field which is equal to the recommended force, that means this correction will be equal to 0. But if you're applying a different force, then it means there will be a correction and you need to account for it. So PM and P naught are discussed. L is again the length of the tape, the total length of the tape, and not the length that you are measuring. A is the cross-sectional area of the tape, and E is the Young's modulus. So combined EA, this product gives you the stiffness. So that basically tells you how much deformation is there in the tape on the amount of pull that you are applying. So when you apply this equation, you need to take care of the units. So you need to make sure that area, Young's modulus, length, all are in the same unit so that the correction that you get is correct. Then the next correction that you have to apply is the slope correction. So the corrections that we have discussed before, the pull correction and the temperature correction can be positive or negative depending on uh, in the case of pull correction, if PM is more than or less than P naught, so you can get a positive correction or a negative correction. Similarly, in the temperature correction, you can get either a positive correction or a negative correction. But in slope, you always get a negative correction because let's say you have the slope and you want to measure the distance between the points A and point B. Uh, and what we are interested in is the linear distance, the horizontal distance between point A and point B. And what the measuring tape will give you, it gives you the sloping distance. So if you cut out a section and draw this right angle triangle, so what we are interested in is this distance AC, which is the horizontal distance between the point A and point B. But what the measuring tape is giving you is the sloping distance AB, which is basically the hypotenuse. And the hypotenuse is always greater than the base. So the correction that we would be applying would always be a negative correction. It's always negative because the distance AC which we want to measure is always lesser than the distance AB which the tape is giving us, and the correction that we will apply will always be the negative. And the correction is given by CH, which is the slope correction, H square over 2L, where H is the vertical distance between the points A and B, the height difference. And how can we measure this? We will cover this in the topic of leveling that we will study later on. And L is again the length of the tape. And this correction will always be negative. So this equation gives you a positive correction, but you need to apply a negative sign with it every time. And then we have a Sac correction. So what is Sac correction? In order to understand this, you have to see this figure. So let's say you want to measure the distance between this point and this point, and usually we place the tape on the ground so that it is along the ground and there is no sag. But when you place it on the ground, there is this other fear that the ground is not straight, it's in a slope. So you will introduce that slope correction into it. So we raise it a little in the air. So that means that the distance that you're measuring is actually horizontal. But what happens is when you place one end of the measuring tape at this point and the other end at this point, there will be a sag. So whenever you've seen this in wires that you hang outside, due to the self weight of the material, you always get this sag. And that means that the distance that you want to measure is the straight one, but the distance that the tape is giving you is the distance along that sag of the tape, which is due to the self weight. So that means the distance that the tape is giving you is more, but the distance that you should get is actually lesser. So that entails that the sag correction is also always negative. So the equation that we have for sag correction is given by Cs, and this equation is equal to the length of the tape, total length, times the total weight of the tape, which is W. So sometimes the weight is given to you in terms of unit length. So this much grams per this much length. So you need to always convert that into total weight by multiplying that weight per unit length by the total length of the tape, and that would give you the total weight of the tape. And since the sag is actually a function of the self weight, so that means we need to take care of this factor of weight. Divided by 24 n squared. This n is the number of spans. Before I talk about the number of spans, let's see this other factor, which is Pm, which is the pull applied during the measurement. Why do we have this factor coming into this equation? Is because the more pull you apply, the lesser will be the sag. That means the more stretch there is, the lesser the sag correction. So that is why we have this factor, and it is in the denominator. So more the pull, lesser the sag correction. More the weight, more the sag correction. Now we talk about the spans. Let's say instead of measuring this distance in one length, in one go of the tape, I introduce another point over here. So first I measure this distance from this point to this point, and then I measure this distance from this point to this point. So what I have done is that instead of measuring this in one go, I'm measuring this in two segments. And when you introduce more segments, the sag keeps on decreasing. So this total sag correction that I will get by introducing more spans will be lesser than the total correction that I get if I just have one span. So this n gives you the number of spans. So again, this is in the denominator. So the more the spans, lesser the correction. So if I have the whole measurement in one go, this n would be equal to 1. So this factor wouldn't do much in the equation. But if I have more number of spans, and again, the number of spans depends on you, the better, and the sag correction will keep on decreasing. So let's talk about normal tensions. Like we discussed, that the sag correction is actually a function of the pull that you're applying on the tape. So there are two different corrections that we talked about. One was the sag correction, and the other one was the pull correction. And these are the equations for both that we have discussed previously. Now, what is actually happening is that the pull is nullifying the effect of the sag. And if we can, using the constants that we have, come up with a value of the pull at which the sag correction is equal to pull correction, we can actually get rid of the both at the same time. So in order to find out that value of the pull, or the force or the normal tension that you're applying, at which the two become equal, so that means the total correction would be equal to 0. So we need to find out the value of that force that we have to apply so that this left hand side of the equation becomes equal to the right hand side. So for that, all the other factors would be a constant, and we can solve this equation for Pm, and we can find out the normal tension that we will apply, at which the pull correction becomes equal to the sag correction and the total correction becomes equal to 0. So that was all about the corrections that we have to apply, and in the next lecture we will talk about